Okay, so the talk of today will be about an introduction to birational geometry. So we will discuss the minimal model program and yes, some related problems also, like Taka conjecture and positivity of direct image sheaf, etc. Okay, so the content of the talk is divided in 3 parts. So first, as I said, I will give an introduction to birational geometry, and we discuss MMP. And for the second part, I want to give you some results on the positivity of direct image sheaf. Okay, so birational geometry is a field of algebraic geometry. So this field is independent on Grothendieck schools. So this field is independent to EGA, SGA. So we can do birational geometry assuming we don't know Grothendieck abstract algebraic geometry. Okay. So this field is studied by Italian school for the case of surface before the birth of Grothendieck, and for higher dimension studied 40 years ago by Japanese school. Okay, so algebraic geometry is a study of geometric object defined by polynomial equation. So in this talk, we will consider complex varieties. So we define affine varieties in Cn as the vanishing of the polynomial equation. So we have an polynomial equation, and we take the set of 0 or of this equation. Okay, so for example, we take y minus x2 is equal to 0 in C2. So this is an affine variety by definition. So the projective space CPN is a natural compactification obtaining by adding the hyperplane at the infinity. So we know that the projective space is defined by C star action. So we take Cn plus 1 minus 0, and the C star action is defined as so the point x0 until xn is equivalent to lambda x0 until lambda xn for any non-constant lambda, non-zero constant lambda in C star. Okay. Yeah. So we remark that Cn corresponds to the set of point 1, so we fix x0 equal to 1, and we move all the number x1 until xn. So this is a subset in CPN, and there is homeomorphism for this subset to Cn, and H. So H is hyperplane in CPN, so this is CPN minus 1, and we can see that CPN minus 1 is identified to this set. Okay, so we then consider projective varieties X in CPN defined by homogeneous polynomial, and we define an homogeneous polynomial of degree R if f lambda x0 and lambda xn is equal to lambda power r times f time our function or our polynomial. So then f lambda x0 and lambda xn is equal to 0 if and only if f is equal to 0 in this point. So from now we consider only the projective varieties. That's mean the zero set of polynomial equation is CPN. So, and if you don't specify, we will assume that X is irreducible and smooth. So, and this is a complex manifold. So irreducible, that means that we cannot write these varieties as disjoint to closed subset. Okay. So, for example, yes. So the set of point x and y in C2 such that xy is equal to 0 is not irreducible, because we can write this set as a union of two closed subsets. So x equal to 0 and y equal to 0. Okay. So we note Cx by fractional. So Cx is a phi of rational function. That means a quotient of two rational functions, such that the denominator q is not 0. And we say that two varieties are birational if they have isomorphic open subsets. Okay. Yeah. So now I state fundamental theorem in birational geometry. So this is due to Hironaka. So the statement is as follows. So every varieties x in CPN is birational to a smooth varieties. That means you take any singular variety in CPN, any singular projective varieties. So we can find a birational model for this varieties, and this model is given by a finite sequence of blow-ups along subvarieties. Okay, so we start with x, we take blow-ups n times. So we will arrive at the varieties x prime such that x prime is smooth. So this is very standard result or basic result. Okay. So, but this is not true for characteristic positive. So this is not trivial. So I think recently, maybe 4 or 5 years ago, some professors sketched that Hironaka resolution of singularities should work for characteristic positive. But this preprint is not published yet, so I don't know if it will be accepted or not. Okay, so so now we take two smooth varieties, z in x, and then we take a blow-ups along the subvarieties z of x. So we can see that so the exceptional divisor is exactly the projectivization of the normal vector bundle. Okay. Yeah. So the geometry of varieties x is studied in terms of the canonical line bundle, because this is a canonical object, so related to the variety. So we take a tangent bundle of these varieties, we take the dual of this, and we take the determinant. So the determinant is scaled a canonical line bundle. And of particular importance, we consider the canonical ring, because people verify that it is a birational invariant of smooth projective varieties. Okay. Now we will define Kodaira dimension. So this is very important notion in this file. So everybody should know this notion. Okay, so we define a rational map by a linear system. So what does it mean, a linear system? So we take, as I said, the canonical line bundle. So this line bundle is correspondent to a divisor, okay, because it is Cartier. And the linear system of this divisor is exactly the set of effective divisor. So divisor such that all the coefficients are positive, which is linearly equivalent. Okay. And by this linear system, we can define this rational map. And Kodaira defined his dimension as the maximum of the dimension of the image of all these rational maps. Okay, so if the linear system is empty, that means that there are no effective divisor, and this implies there are no section, so there are no rational map. So in this case, by convention, we assume that the Kodaira dimension is minus infinity. Okay, so as an easy exercise, you can see that the Kodaira dimension is the limit suit of this fraction. So you take a logarithmic of the set of section, and we divide this by the logarithmic of m. Okay, so we know that complex projective manifold have no non-constant global holomorphic function because are compact. So there are no global section, which is not constant. So so it is natural to consider global section of line bundles. And as I said, there is only one natural choice, which is the canonical line bundle, because it is related directly to the variety. Okay, for example, if you take X is equal to CPN, so the projective space, so we know that the canonical line bundle is the O minus n minus 1, and n is the dimension of X. So by O1, I mean the tautological line bundle. So we take the dual, and after that we take n plus 1. We twist with itself n plus 1 times. Okay, so if X is a smooth hypersurface of degree k, okay, that means a subvariety of codimension 1 with degree k. So then by adjunction formula, you can see that the canonical line bundle is O of k minus 1 minus l restricted in X. Okay. So let's discuss the geometry of curve. So a curve, a complex projective curve is a Riemann surface. Okay. So when dimension of X is equal to 1, we say that X is a curve, and we have three cases. So the first one, when the Kodaira dimension is minus infinity. So that means exactly there are no section. Okay. And by Riemann-Roch, so this is a very known formula, we can see that the genius is equal to 0. So this means that X is CP1. Okay. And by calculation, before, the canonical line bundle is O minus 2. So if the Kodaira dimension is 0, so we can see that the genius is equal to 1, and this is an elliptic curve. Okay, and we know that for elliptic curve, the canonical line bundle is trivial. And when the Kodaira dimension is equal to 1, then we say that X is a curve of general type. And by definition, omega X is big. So big means exactly that the varieties is of general type. And the Kodaira dimension is maximal, because the Kodaira dimension is between 0 and the dimension of the varieties. And when there is no section, by convention, we say that Kodaira dimension is minus infinity. Okay, this is good. So yes, to see that final generation of the canonical ring, we need to discuss this lemma. So we take a divisor on a curve. So a divisor means that a sum of a coefficient times a point. Okay. So we take a divisor on a curve of genius G, any curve. So if the degree of D is bigger than 2G, so 2 times the genius, so the linear system has no base point. So that means exactly that all the section of this divisor cannot equal to 0 at the same time. Okay, so in this case, the rational map defined by Kodaira is a morphism. Okay, this is not rational. So the map is defined in every point. Okay, if the degree of D is bigger than 2G plus 1, so then D is very ample. Very ample means that the section give an embedding in CPN. So we embed every curve to CPN. So by this divisor. Okay, so for the genus, for curve of genus G bigger than 2, we see by the lemma above that the pluricanonical bundle is very ample if M is bigger than 3. So we take the second point in the lemma, and we can see that for M bigger than 3, so this is very ample because the degree of omega x is 2G minus 2. So when we multiply by M, so and M bigger than 3, so this is very easy. Okay, so this means that if we take section or which are a basis of this vector space, which is the set of section, so then we have an embedding, and we can see that this line bundle omega x times twisted M times, so it's exactly a pullback of O1 of CPN by this morphism. And in particular, the canonical ring is finitely generated because for every M prime, which is bigger than M, we have the same embedding. So all the section are writing as this previous section. So this is good. Yeah, so this is finitely generated. Okay, so yeah, so now we can see the classification of the curve. So I said that if the Kodaira dimension is minus infinity, so the curve is CP1, and if the Kodaira dimension is equal to 0, the curve is elliptic curve, and if the Kodaira dimension is equal to 1, the curve is of general type. That means Riemann surface of genus bigger than 2. Okay. So now we like to prove similar result in higher dimension. So if the dimension of X is bigger than 2, the birational equivalence relation is not trivial. What does it mean, this sentence? So that means exactly we can have two surface or varieties of higher dimension which are birational but not isomorphic. Okay. And for curve, this is not the case. So birational curve are always isomorphic. So we can say that the birational equivalence is trivial for curve. Okay, so the minimal model program. So this is very beautiful program. So start from surface. Okay, so we hope to find a good representative of X or a birational varieties X prime of X with the canonical bundle positive. Okay, so the idea is to find a good birational representative of the class which has beautiful properties, and we will study this. Okay, this is the goal. Okay, so let's discuss the case of surface, and after that we talk about some advanced topics. Okay, so let S be a surface and P is a point. So then there exists a surface S prime, which is the blow up of S in the point, and the morphism from S hat to S, which is unique up to isomorphism. So such that the restriction of the pre-image of S minus this point is isomorphism, isomorphic to S minus this point. That means outside this point we have the same set. Okay, but in the point this is the exceptional divisor. So and we can see that this exceptional divisor is CP1 because we take blow-ups on a point. So we replace this point by CP1. Okay. So we consider irreducible curve. That means a curve which cannot be written as union of two closed subset that pass through point P with multiplicity M. So the closure of the pre-image of C minus P in S hat is irreducible curve, and we call this by strict transform of C. Okay, so by local calculation, we can see that the okay, so and there is an isomorphism between the Picard group of the blow-ups and the Picard group of S plus Z. So that means exactly that when we take blow-ups, the Picard group grows. Okay, so and this isomorphism is defined by this map. Okay. Okay, so for any divisor D and D prime on S, so the pullback of D, so the intersection theory is preserved when we take blow up or when we take birational morphism. So that means that we take blow up of D, the pullback of D, we intersect this with the pullback of D prime. That is exactly D times D prime. Okay. Okay. Yes. Let's discuss some basic theorems. So let's be a rational map from surface of projective varieties. So that means a map which is not everywhere defined. Okay. So then there exists a surface as prime, a morphism as prime to S, which is the composite of finite number of blow-ups, and the morphism as prime to X. So what does it mean, this theorem? So that means exactly that we can resolve the indeterminacy locus of the map. So the map is not defined. So we take a finite sequence of blow-ups. So, and after we get a map which is everywhere defined. Okay. So yes, now I state a very important result. So very fundamental result. So it's due to Castelnuovo. Castelnuovo is Italian. So yes. So let S be a surface and E be a curve is isomorphic to CP1 with self-intersection is equal to 1. So then E is an exceptional curve or a -1 curve on S. Okay. So by this theorem, we can see that always we can contract all the -1 curve. That means we start with a surface S, which don't have good properties, like the canonical divisor is not positive. So by this theorem, we can contract all the -1 curve, and we can see that the process termine, and we get a good minimal model for this surface by this principle. So this is very important. So what I mean by a minimal model? So the minimal model of a surface S is a surface S prime, such that does not have -1 curve. As I said, we contract all the -1 curve, and we can see that the process finished. So the minimal model of surface always exists. And as a basic fact also, when the quadrilateral dimension of the surface is positive, so S doesn't have -1 curve, that means exactly that the canonical divisor is null. So what does it mean null? Null means that we intersect this divisor by any curve. So this is always positive. So we take any curve in S, okay? So we can take so reduced irreducible curve, okay, in S, we intersect this curve with this divisor, the canonical divisor. This is always positive. So if it is positive, so this means that the canonical divisor is null. Okay. Donc, so nulleness is very important in birational geometry, because after some power will be semi-ample, and you can have some rational, some morphism to CPN, and this varieties is very simple to study. Okay. Yeah. And so let now discuss MMP program for a surface. So this is known by Italian school. Okay. So a surface S is ruled by definition if it is birationally equivalent to a curve times CP1. Okay. And real surface are only the surface with Kodaira dimension minus infinity. So all the surface with Kodaira dimension is equal to minus infinity are always ruled. That means birationally equivalent to C times CP1. So if C is a smooth irrational curve, that means that C is not CP1. So the projective rank 2 bundle are minimal. So that means there are no -1 curve. Okay. And the last point, 5, if C is projective line, I can give you some counterexample. So if E is O1, so here O plus, so O1 plus the trivial bundle. So we take projectivization of this. So the projectivization is identified to the blowups of CP2 in the point. And you know that the blowups of CP2 in the point is not minimal, because the exceptional divisor or the exceptional curve is -1 curve, right? Because E squared is always equal to -1. And yeah. Okay, so the minimal model is not unique when S is ruled. Okay, so yeah, so the only surface, for example, the only surface geometrically ruled over CP1, so this surface are Cayled rational surface, okay, are the Heisenberg surface, so it is the projectivization of O1 times twisted and times plus the trivial bundle, okay. So it is well known that the Picard group of this surface are Z2. So generated by the class of O1 and the class of the fiber. And you know that the fiber here is isomorphic to CP1. Okay. So if N is strictly positive, then there is a unique irreducible curve B on this Heisenberg surface with the negative self-intersection. So if B is the class of this irreducible curve in the Picard group, so the self-intersection of this curve is -n. So for example, if we take projectivization of O1 plus the trivial bundle, we can always have or there exists always unique reducible curve with self-intersection is equal to -1. So this is -1 curve, and this means that the F1 is not minimal. But by this fact, you can see that Fn are always minimal except for n is equal to 1. Okay, and all these surfaces are birational, but not isomorphic. Okay, so what does it mean? So in this class of we can find a lot of minimal surface which are not isomorphic. So there are an infinity minimal model. So the minimal model for a surface is not unique by this example. Okay. Okay, so what we can conclude here, we can conclude that the minimal model of periodic surface is the projectivization of rank 2 vector bundle. And when C is rational, that means that C is CP1, we can take the Heisenberg surface. Okay, but when when the Kodaira dimension is positive, the situation is different. So we take here S be a minimal surface with the Kodaira dimension is equal to 0. So then as a fundamental result, K square is linearly equivalent to 0. That means that the canonical divisor, the canonical line bundle, has a torsion. So when we take when we twist this canonical line bundle by itself, so we get the trivial line bundle. Okay, and we can see that the Euler holomorphic Euler characteristic is positive also. Okay, so for this type of surface, there is a unique minimal model, and this unique minimal model is here but it's related with some invariant as geometric genius and the irregularities. So if the geometric genius is equal to 0, so what does it mean, geometric genius? So the geometric genius means exactly the H2 of the trivial bundle. So if this invariant is equal to 0 and the irregularity is 0, so irregularity means H1, okay? H1 of the trivial bundle. So then the surface is an elliptic surface. So if the geometric genius is equal to 0 and the irregularity is 1, so the surface is B elliptic surface. And when the geometric genius is equal to 1 and the irregularity is 0, so we can see that the canonical bundle is trivial, and this type of surface are K3 surface. So, and K3 surface also are simply connected. Okay, so if the geometric genius is equal to 1 and the irregularity is 2, so S is abelian. So there are no minimal surface of Kodaira dimension is equal to 0 with the geometric genius is equal to 1 and the irregularity is equal to 1. Okay, so we can see that I skip this case because there are no surface which verifies these properties. Okay, so if S is a minimal surface with the Kodaira dimension is equal to 1, so then the self-intersection of the canonical bundle is trivial, and this surface verifies nice properties. What is this property? So there exists a curve B and surjective morphism with connected fibers. So all the fibers are connected, such that the general fiber is an elliptic curve. Okay, and when S is a minimal surface with the Kodaira dimension is equal to 2, so then the canonical bundle is big, and this surface is scaled of general type. Okay, so we finished the surface case by a nice result. So this result is due to Bogomolov, Miyauka, and Yao. Okay, so just I want to state Yao. So Yao is a very strong mathematician, and as I know, he is the most so the geometer the most cited in the world. So for example, more than Gromov and Grothendieck. Okay, so if S is be a surface of general type, so then Bogomolov, Miyauka, and Yao so proved the following inequalities. So this is very nice inequalities because so these inequalities relate the positivity of the varieties and the topology of the varieties. So the inequality is what? So C1 squared. So the first class share, the square of this is less than 3 times C2. So C2 describes the topology. So C2 is just the Euler characteristic, and C1 squared describes the positivity of the varieties. Okay. Okay. Yeah. So generalizing this picture. So okay, what we can conclude here? We can conclude that the minimal model always exists, and people are studying this model before the work of Japanese school, and now the question is if we can generalize the picture in higher dimension. And the problem was when we can see that Castelnuovo principle doesn't work for higher dimension. So we cannot characterize the rational curve by Castelnuovo principle. So generalizing this picture to higher dimension is a hard problem, okay, which was solved in dimension 3 case by case, okay, 40 years ago by the work of Mori. So Mori, for his work, he owned his Fields medal, and Kawamata also did a lot of progress. Kohler and Russian people like Reid and Shokorov. So Shokorov is advisor of Berka. So Berka also owned Fields medal. Okay, so and the program is finished in dimension 4 by Shokorov. Okay, so the start point was when Mori proved the famous Hartshorne conjecture. So what is this conjecture? So the statement is very basic. So if X is a smooth projective varieties over C, yes, so over complex number. So if the tangent bundle is ample, so Hartshorne say that X should be a projective space. So what does it mean, an ample vector bundle? So ample means exactly we take projectivization of this, and we take the total logical line bundle, O1. So if O1 is ample, this is by definition means Tx is ample. The tangent bundle is ample. So Mori proved this conjecture, and by his very known principle called Van-der-Breek principle. Okay. So Mori discovered his famous theorems about the existence of rational curve. So when he proved this conjecture, after that, directly he gives some theorem which locate the rational curve. Or so what is so Mori had a lot of results in this direction. So for example, if X is smooth projective varieties and minus Kx is ample, that means X is Fano varieties. So then X contains a rational curve. So Mori said that for this type of varieties, X has a rational curve, and for any point of X, we can find the rational curve, okay, such that the intersection of this curve with minus Kx is less than the dimension of X plus 1. So he by this theorem he said that he can see the geometry of the rational curve on the projective varieties. And more generally, so if the variety is not Fano, he had also some result, like we take X as smooth projective varieties and H is an ample divisor on X. So we assume that there is a irreducible curve C prime in X, such that the intersection of C prime and Kx is negative. Okay, So he can locate the negative curve, the rational negative curve. So so then there is a rational curve E in X, which has the same properties of the theorem 1, and with another result, which will be very helpful to see the Kohn theorem, Mori Kohn theorem. Okay, so following these last theorems, Mori proved the Kohn theorem, which was the major step in MMP. So what is the Kohn theorem? So let's introduce some notation. So if B is a R vector space, a subset N in V is scaled the Kohn if it contains the zero, and N is closed under multiplication by positive scalars. Okay, a subcon M is scaled extremal if we take two elements U and V in N such that the sum is in M. So this implies that U and V are in M. Okay, that means that the extremal subcon is in the boundary in some sense. So M is scaled an extremal face of N. Okay, and one-dimensional extremal subcon is scaled an extremal rays. So these extremal rays are very important for MMP in higher dimension. Okay, one cycle is a formal linear combination of reducible curve. One cycle with real coefficient modulo numerical equivalence forms an R vector space, and it is denoted by N1. Okay, so N1 is by a good perfect pairing. We can see that N1 is a dual of the near-Siberi group, and this implies that N1 is a finite dimensional vector space, because by Euler spectral sequence we can see that the near-Siberi group is included in H2, so and H2 is of finite dimension. So this means that N1 also is of finite dimension. Okay, so now we define the numerical or the effective Kohn. So that's mean the Kohn of the cycle written as the sum of AI, the class of CI and II are always positive. And we take the closure of this. So the closure of this is called the Kohn of curve. Okay. Okay. So now we discuss the Mori Kohn theorem. So this was a fundamental result to finish MMP in higher dimension. Okay, so what is the statement? So we take X as smooth projective varieties. So then there are countably many rational curve CI such that intersection of CI and Kx is negative, and the effective Kohn is decomposed in two parts. So when Kx is positive and when Kx is negative, this negative part is written as a sum of the class of this rational curve. Okay, so this theorem means exactly that the rational curve is the only curve are important for MMP because they contribute for the negative part. So every curve which is negative is included in some class of rational curve. Okay, so this is very interesting. So when we contract the extreme arrays for smooth projective varieties in higher dimensions, some singularities appears, so which scale a terminal. Okay, so now I want to define these terminal singularities in the more general picture, So here we consider a pair X and D, and the reason that we consider a pair is to finish MMP by induction. So we take we study varieties as a pair. So we take varieties and a divisor and you know that divisor is of dimension 1. So this is the reason that we take always a pair. So a log pair is a normal varieties. So normal varieties means varieties which is singular, and the singularity is good. That means that the local ring is normal in the algebra definition. So with the Q divisor D positive, such that Kx plus D is Q Cartier. So Cartier with Q Cartier is very important, because for this divisor we can consider a line bundle which correspond to this divisor. Okay, so a birational morphism G from Y to X is a log resolution, so or log resolution of Aeronaka of the pair XD if G is projective, so means that Y is projective and Y is smooth, and the exceptional locus is a divisor, and the pre-image of G union the exceptional set of G is a divisor with global normal crossing support. So that means that this divisor is like this. So they intersect as xy is equal to 0 in C2. So, okay. So this is very important for local calculation. Okay. So always we have this formula. The canonical divisor y plus d is the pullback of kx plus d. And the pair xd is Kawamata log terminal, so means that the singularity is Kawamata log terminal if for every log resolution, and equivalently we can verify this just for one, because this is independent to the resolution. So the coefficient of delta are strictly less than 1. Okay. So so this is the definition of Kawamata log terminal. And this singularities appears when we contract extreme arrays. So this is the reason that we define this type of singularities. So if X is a normal varieties, we say that X is minimal. If X has terminal singularities, and as in the surface case, the canonical divisor is nef. Okay. So here we add just a condition of singularities, that singularities are terminal, because this type of singularities appears. Okay.
Sorry, excuse me, Houari.
Yeah. I want just to finish 1 or 2 slides, and we can take a break.
Okay.
Okay.
Thank you.
Because I plan to finish MMP in the first part. So I think there is, yeah, there is just 2 or 3 slides. I can finish that very quickly. Okay.
Thank you.
Okay. So now we define a very important transformation or in MMP program, which is called the flip. So a flip is defined by Shukorov in some sense, or Shukorov Mori also. Mori did. So Mori also has some intuition. Okay, so F is a proper birational morphism between normal varieties, so that the exceptional set has codimension at least 2 in X. So if you assume that Kx is Q Cartier and minus Kx is relatively ample, so that means that the intersection of Kx and the curve which are in the fiber is negative. So or minus Kx times a curve in the fiber are positive, strictly positive. So a varieties X plus with the proper birational morphism is scaled the flip. If Kx plus is Q Cartier and Kx plus is relatively ample, and the exceptional set has codimension at least 2 in X plus. Okay, so by why we need this operation or this transformation is just to skip the rational curve. So we want to find the model which is scaled flip, and this negative curve disappear. Okay, this is very important for a contraction, because after that we have some bed contraction, so we need to take flip. So the main goal of this program is to show that given any n-dimensional smooth complex projective varieties X, we have, if the Kodaira dimension is positive, then there exists a minimal model. So that is a varieties Y birational to X, such that the canonical is enough. And if the Kodaira dimension is minus infinity, so we want to have a varieties Y birational to X, which admit Fano vibration. So this is as in the surface case. So we remember that in the surface case, when the Kodaira dimension is minus infinity, the surface are always ruled. So this is what we hope here. Okay. Okay. So I want to describe the process very quickly. So if we take if Kx is not enough, because we want Kx is enough, so we need to contract some extremal arrays. So by the Count theorem, there is a rational curve such that the intersection is negative, and the morphism which contracts this curve. Okay, and there are three possibilities. So if the dimension of z is less than dimension of x, so this is the required Fano vibration. And if the dimension of z is equal to the dimension of x and f contracted divisor, then we say that f is divisorial contraction. And this is a good contraction because the canonical divisor is Q Cartier here. And we can take intersection theory, etc. So this is good contraction. And if the dimension of z equal to dimension of x and f doesn't not contract a divisor, so we should take a flip. Okay, and the problem, so there are a lot of problems in MMP. One of the problem, if the flip exists and the flip determination is here. So how many times we can take this process? Okay. Yes, because we want to contract extreme arrays, and we know that in the Count theorem, this negative part, so the sum is from 1 to infinity. So there are we don't know how many contractions that we can have. Okay, so yeah, just I want to finish this part by a very very famous theorem, and this theorems so proved by Birker, Cassini, Heiken, McKernan. So for these theorems, Birker on his Fields medal also, and Birker after that do some things like the boundness of the modular space of log Fano and etc. So okay, so Heiken and McKernan have shown that assuming the minimal model program in dimension n-1, so then flip exists in dimension of n. So yeah, so we want to have inductive approach for this MMP. So okay, so what we prove Birka, Cassini, Heiken, McKernan. So we start with Kawamata log terminal pair because the singularities appeared in MMP. So if Kx plus d is Q Cartier, and here we define everything relatively, okay, for many reasons. So we take P a map from X to U, which is a projective morphism of projective varieties. So if either D is relatively big and Kx plus D is relatively pseudo-effective, or Kx plus D is relatively big. So what does it mean big? So we remember that big is that means that the varieties of general types. So for general types varieties, BCHM prove the minimum, prove MMP. So the flip exit determination is here, and the good model is here also. So they prove that Kx plus D has log terminal models, and Kx plus D has log canonical models. That means exactly that this relative canonical divisor plus D is semi-ample. So we can take a morphism to CPN and we study these varieties. And the global generation is here. But the global generation proved also by Su using the Mai approach and his approach, analytic approach. Okay. And okay, I finished this part by see what happened for a very smooth picture or very restricted picture. So if X is smooth projective varieties of general type, so then X has a minimal model and X has canonical model, and the canonical ring is finitely generated. And also X has a model with Kähler-Einstein metric. So this metric is very important. So it's related to K stability, and yes, this notion is defined by Tian, student of Yao, and Donaldson also. Okay, so let's take a break.
Okay, thank you very much, Houari.